Concrete is one of the most used materials on the planet, and in this video I'd like to talk about some of the latest developments in concrete technology, or what we are currently thinking to be the new normal. So we start by defining what concrete technology is. And to clearly understand what concrete technology is, it means we must achieve an understanding of the individual materials that make up concrete. And these perhaps are known by everyone to be the cement, the sand, the aggregates, and water. And just understanding those individual materials is not enough. But in addition, we must be able to understand the behavior of the composite that make up the what? The concrete. How do they relate? How does the sand relate with the water? How does the water relate with the cement? And how does the entire composite material that we call concrete relate? And in addition, we must be able to understand that concrete is oftentimes not used as a standalone material, but it is embedded with other elements or other materials. Secondly, we must understand the techniques employed in handling concrete as a material. And this means that we must be able to understand the mixing process, the transportation process, the formwork, the placing, the vibration, the curing, and the so many other entities that are involved in the workings of concrete. Thirdly, we must understand the relationship between the hardened concrete material itself and the environment in which it is placed. This is important if we are to consider things like durability characteristics, which is going to be defined by the service life of the concrete structure, and eventually the performance. The relationship between these different aspects of concrete, the handling, the mixing, the materials, the durability, and the environment, and how they relate with each other are going to be key in the understanding of how concrete works. So it becomes clear that to achieve an understanding of concrete, there are two ways to look at it, and these are definitely varied schools of opinion. There are some people who start from the whole to understand the part, and there are those that prefer to start from the part and be able to understand the whole entity. In this case, I'll just use an example of just a unidirectional approach. For example, starting from the whole to understand the basics of how concrete works and how it interacts within the environment or with the various environmental considerations. When we look at the whole, for example, look at a concrete structure. That big concrete structure, be it a beam or be it a bridge structure or some pier within the seabed or within the river or wherever it is, of scales greater than a meter or so, then this is what is directly interfacing with the environment. All the actions of the environment are being felt by this big structure. So the loads, the environmental actions are then extended to the material itself, to the respective constituents of concrete itself, the mortar and aggregate composite. So from there now we start to understand how, if you're talking about, for example, external loads, how are they transferred through the concrete? How is the reinforcement reacting to that? How about the aggregates themselves, and how is the load distributed through the concrete? Then we try to understand each and every of those aspects until we reach the smallest scale to know how the various constituents of concrete, from the mortar to the aggregate to the different cement hydration products, and how they are able to actually contribute to the behavior of our entire structure. In other words, if we understand how this structure behaves, then we can be able to tell how the various small components of concrete are contributing to that. So we can now adjust, for example, the ingredients and study the behaviors of the bigger structure. So in other words, what we are talking about here is that the structure behavior could be based on the microphysical information of these small elements within the concrete, and those are the ones that are able to actually decide or define the properties of the whole in general. So understanding what these properties are is essential. Whether we understand how the reinforcement behaves or how it interacts with the alkalinity within the concrete will be very crucial to the understanding of the mechanisms that are involved. It's the same approach we use when we try to understand how concrete behaves from the hydration stage to when it develops the initial defects such as plastic shrinkage cracks, photogeneous shrinkage cracks, and so on and so forth, drying cracks, structure use loads, environment, carbonation, corrosion, and so on and so forth. So we try to engage the various relationships between the environment in which the concrete is exposed and the various constituents of the concrete. So if you're looking at a dry and wetting environment, or a windy or sunlight, or one which is exposed to a corrosive environment, how do the various constituents, the reinforcements within the concrete, the aggregates, the hydrated cement, how do they respond to those environmental considerations? And then we can be able to carry out or to develop theories or develop models and make simulations to understand how those processes work. Anyway, with that in mind, we now come to understand that we are, at least in this present day and age, we are able to deal or to produce some of the best concrete, things like high performance concrete, ultra high performance concrete, ultra high performance fiber reinforced concrete. I've been reading about ultra high performance fiber reinforced concrete, and I came across some of these results by a group in Japan that have developed a high performance ultra high fiber reinforced concrete, and they have achieved quite high strength, as you can see here in red, the compressive strength of over 300 or of over 250 megapascals. I think this is quite commendable for concrete which does not have reinforcement bars. If you look at the fiber volumes of 1 and 2% that have been used in this concrete, and then you look at the resulting split cylinder strength and the Young's modulus, then you'll be able to appreciate the achievements we've been able to get as far as concrete technology is concerned. So if you look at these failed specimens in compression, then you see that these are really samples that are a result of high strength failure. They have already used some of this concrete to build this Mirai Bridge in Japan. It's a PC box girder bridge and weighs about 53 tons. It's a 49.4 meter span with a slab thickness of 5 centimeters. Can you imagine? A slab thickness of 5 centimeters, no reinforcement bars. Web is just 8 centimeters. And this is just a foot bridge that is going over this water body, as you can see. So the potential for us to exploit the advantages that come with ultra high performance fiber reinforced concrete alone are enormous. It's actually exciting to see the direction concrete technology is taking. This is one of the details during the construction of this bridge. Of course, all these elements are precast elements in controlled conditions. That's why they are able to achieve such high-end product. What we are saying here is that with a certain volume of steel fibers, we can be able to get away with traditional reinforcing bars and be able to come up with concrete with high strength, high durability, and high ductility. And you can imagine, you look at the shapes and the dimensioning of 5 centimeters for a slab thickness, 8 centimeters for a web. For such, even if it's a footbridge, that is, but the span alone of about 50 meters, I think that's a great achievement so far, given that there are no reinforcement bars that have been used in this. Anyway, similar projects are designed and they are on course to being built, and they are finding applications such as in slender elements, for example, bridge decks, slabs, columns, and several other lightweight members. As you can see in some of these illustrations, we're having webs of just 15 centimeters and slab thicknesses of 15 centimeters for bridge decks and road bridges. I think this is a great achievement or noticeable progress in concrete technology. As a bonus, I'll try and briefly look at some of the what are proposed as high performance concrete. This is crack self-healing concrete, which is supposed to be concrete that is able to fully recover any of the formed cracks. So crack self-healing concrete actually is supposed to be able to close cracks that have been formed through various mechanisms such as deposition of calcium carbonate or through different self-healing methods. I'll make a completely separate video on crack self-healing concrete because this for me has been a subject of interest for the last 5 years. Then we have self-compacting concrete. This is also another special type of concrete. Those of you who have watched one of my first videos here, it's on self-compacting concrete that I've developed a lot of interest with, and it was one of my projects that I worked on, trying to actually incorporate a self-healing effect in self-compacting concrete. I think this is one of the exciting types of concrete. It is self-leveling. You pour it and it will fill into any gaps, even in the congested reinforcements. Then we have another special type of concrete which is definitely within the category of high performance or ultra high performance concrete. This is fiber reinforced concrete. I mentioned in some of the ultra high performance concrete that is being done for the footbridge, that they're using steel fibers to actually realize concrete without reinforcement bars. And so in conclusion, or to wind up, I think the future is already here. We are already seeing that we are developing already remote structure health and monitoring systems, self-sensing and self-repairing structures. We are already talking of high performance, ultra high performance. We are embedding in artificial intelligence to study our concrete structures and their performance. Hybrid structure systems are already something of the future that is being implemented. And if we are looking ahead, for those of us who will make it to Mars, then we are starting to think of space colonization and what structural requirements we will have to develop while there. We need to be ready to develop new materials based on the raw materials that will be present at those new planets that we discover. And in this system, you can be able to see that if we have a structure that is embedded with some of these technologies, we can be able to remotely monitor the behavior or the changes or the structural responses of such a structure and be able to understand when and how and what kind of repair or what's the behavior the structure is experiencing, or what is necessary, what is the rate of deterioration, what kind of repair mechanism is necessary, or what is taking place, and so on and so forth. This is quite important, especially, for example, after an earthquake, and we need to assess the conditions of the structures. And finally, I leave you with this.